This is the last section in Chapter 10. It's also the last section before our test. So we have already talked about how to think about polar coordinates, how to graph things with polar coordinates, and how to find slopes using polar coordinates, so derivatives. Today we're going to talk about some of the things you would use integrals for, in particular finding areas of regions described by polar equations, and finding the lengths of curves defined by polar equations. Actually, we're not going to do either one of those things in this video, though. In this video, we're just going to do some of the stuff you'll need to do as part of that. The actual formulas for finding areas and lengths we will see in class. You'll also see when you read the book, which you should do. But for this video, we're going to figure out, well, areas and lengths always involve integrals. How do you know which theta values to integrate between? And it's not as easy as figuring out the x or y values to integrate between when you're dealing with Cartesian coordinate stuff. So, for example, let's say here's a problem. Find the area enclosed by one loop of the curve r equals cosine of 2 theta. Well, I don't even really know what that means unless I have a graph, but so one option is have a graph. If you have a graph or you graph it yourself, what you will see is a sort of four-leaf clover looking thing. And I want the area inside one of those loops, so I just have to know what theta values are on either side of one of those loops. So I can think about these two rays coming out from the origin. The origin is also called the pole in polar coordinates. And between those two is one loop. Well, those two rays are at theta equals pi over 4 and theta equals negative pi over 4. So a theta interval that would contain the shaded loop is negative pi over 4 to positive pi over 4. I could have picked any of the other of the four loops and found theta values for it, because by the way the question is expressed, it seems like all those loops have the same area, so any one of them would work. But there's one of them. Okay, what if you don't have a graph? Well, sometimes, when it's fairly simple like this one, you can do all the work you need to do without a graph. One loop of a curve usually means the curve's going to go out in a loop and then come back to the origin, probably multiple times, and we only want to deal with one of those loops. So if you don't have a graph, you can say, well, coming back to the origin means r equals 0. And for this equation, that means cosine of 2 theta equals 0. So I want to find all the angles where cosine of 2 theta equals 0. Which angles have their cosine equal to 0? Well, it's all the odd pi's over 2, right? Pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc. All of those, their cosines are 0. So all of those are candidates for 2 theta. So the graph comes back to the origin, or pole, whenever 2 theta equals one of those numbers, an odd multiple of pi over 2. Well, if 2 theta equals an odd multiple of pi over 2, theta equals an odd multiple of pi over 4, and that means one loop should be whatever the curve does in between two of those odd pi over 4s that come one after the other. So you can pick negative 1 pi over 4 and positive 1 pi over 4, or positive 1 pi over 4 to 3 pi over 4, or 3 pi over 4 to 5 pi over 4, or any odd number pi over 4 to the next odd number pi over 4. Right? So any of those theta intervals will work, and you can see that that gave us the right answer, although it was easier to look at a graph. If you don't have a graph, we could do it this sort of solving equations way. However, if you try to do these without graphs, sometimes you will get wrong information. So it's always good to look at a graph, even if it's a very rough sketch of a graph, just to give you a general idea of what you're looking for. Then you can solve the equations to find exact values. Here's an example. Say I was trying to do this without a graph. I want to find the area inside the curve r equals cosine 2 theta, which I already know looks like a four-leaf clover, but outside r equals a half, which is a circle around the origin with radius a half. Well, to do that, I need to find all the places where those curves intersect, because then I'll need to integrate between the points of intersection to find when one is outside the other. The area where one is outside the other. So I solve for points of intersection, right? If you have in Cartesian coordinates y equals x squared and y equals 5x, to find where they intersect, you would set x squared equals to 5x. So here I have r equals cosine 2 theta and r equals a half. And to find where they intersect, I could set cosine of 2 theta equal to a half. Well, cosine is a half means that the angle is pi over 3 or 5 pi over 3 or 7 pi over 3 or 11 pi over 3 or any odd pi over 3 except for the multiples of 3. Okay, which is a little bit weird, but sure. So that's what 2 theta needs to be, and it could be negative, which means theta should be plus or minus pi over 6, 5 pi over 6, 7 pi over 6, etc. And that means in one time around the circle, 0 to 2 pi, I found 4 theta values. Right, theta equals pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those are the 4 values of theta that I found in between 0 and 2 pi in one time around the circle. But hang on, if you look at a graph, I've got our 4-leaf clover there and the circle of radius a half. There are actually 8 points of intersection. I drew them in black. There's 8 points of intersection, and we only found 4. We found the 4 ones that I'm going to highlight in purple here. I think they got a little bigger and a little purpler. We found 4 of them, but we didn't find all 8. So if we hadn't looked at a graph, if we hadn't known that there should be 8, we would be definitely off on the wrong foot trying to find this area. Right? To find the area, we need all the points of intersection. And to do that, we'd have to use symmetry here, right? It's a symmetric picture. Or we could realize that another equation for the circle, instead of just r equals a half, I could have drawn the same circle by using r equals negative a half, and then solve cosine of 2 theta equals negative a half, and we'd get the other 4 points. Right? So weird things like that can happen where solving the equations doesn't quite work. So it's always a good idea to look at a graph to make sure the answers you got from solving equations to find points of intersection make sense. Here's one final example. If I'm trying to find the area inside the curve r equals 3 sine theta, but outside the curve r equals 1 plus sine theta, what theta values should I be dealing with? What interval for theta? Inside one curve, but outside another. So again, I'm looking for points of intersection. But now I know better, I'm going to first look at a graph. This particular picture that I found of this has the theta values written on it, but imagine those weren't there. What if we didn't have a picture with theta values written on it? Okay, so the theta equals pi over 6 and theta equals 5 pi over 6. Pretend they're not there. All right, from the picture, we see 3 points of intersection of these two curves. Right, the 3 points of intersection are now highlighted. And it turns out that for the area we want, inside r equals 3 sine theta, but outside the cardioid r equals 1 plus sine theta, the area we want is just between 2 of those theta values, the far left one and the far right one. So we want to know the points of intersection that are not at the origin, are not where r equals 0. Okay. So we're going to try solving equations. If it doesn't give us things that make sense for the picture, then we'll try something else. To find points of intersection, again, I can set 1 plus sine theta equal to 3 sine theta. Subtract sine theta from each side, I get 1 equals 2 sine theta. Divide by 2, I get 1/2 equals sine theta. And I know the angles whose sine is a half are pi over 6, 5 pi over 6, and those same angles by different names if you keep adding 2 pi or subtracting 2 pi, more outside of the standard 0 to 2 pi range. Looking at the picture, pi over 6 and 5 pi over 6 are reasonable values for those points of intersection. One of those is approximately in the direction where theta equals pi over 6, and the other one is approximately in the direction where theta equals 5 pi over 6, a little less than pi. So those are probably the right theta values. So those are the right theta values for the 2 desired points of intersection. So the interval we want is the interval between pi over 6 and 5 pi over 6. However, notice that this would not have helped us at all if we needed to know that third point of intersection. If we needed to know the third point of intersection, solving these equations would not have helped, and we'd have had to just look at the picture or do something else to find that third point of intersection. So the moral of the story is solve equations to find points of intersection, or to find where loops come back to the origin, right? To find the theta values you need to integrate between. But don't only depend on solving equations. Look at a graph too. We will talk about what to do with these intervals, what integrals to write down to find these areas, and so on in class. Please also skim the book before class, but I will see you there.